So in this video, I want to talk about what happens when we include control variables in a model that we don't technically need to include if they aren't part of what's known as an adjustment set. So it might be worth watching my other video on the pitfalls of regression, but just to give you a little bit of context, I want to contrast this scenario here where we have a principal variable x and it relates to our outcome y via some linear relationship described by this beta coefficient plus some epsilon. And then we have also a whole load of other independent exogenous quote unquote control variables that also relate to y but have no causal influence on x or between each other. So this is a very simple model. They're all independent variables and they're all related to our outcome y. We can contrast that with a more complicated scenario that might look something like this, where we have say if we consider all these other variables as control variables, you can see that there's other sort of causal mechanisms that exist that make the situation more complicated. And I gave an example in the previous video that if I want to estimate the effect of x on y, controlling for d is a mistake, and actually what we should be doing is looking at finding an adjustment set which comprise variables such as a and k, which block backdoor paths that affect our expectation on the estimate for the relationship between x and y. But I did also mention that, if we control for c here, or include c in quote our adjustment set, then it isn't really part of the adjustment set, and it shouldn't have any impact on the estimation of the effect on x on y. So just going back to a more simple scenario here, I want to investigate the effect of including a, b, c, d, e, and f in a multiple linear regression that's concerned with, or principally concerned with, the estimation of beta x. And so based on the causal analysis that we went through in the other video, we came to the conclusion that we shouldn't need to include any of these variables, and including them will not affect our estimation of beta x. So what happens if we do include them, despite them not being relevant? I see many people talk about sharing the variance. In fact, I mentioned that in the previous video as well. And that's true to an extent. Whatever sort of residual or spurious correlation exists between these variables, controlling for them will sort of end up partitioning that sort of spurious correlation across the variables. But in a truly independent case, there shouldn't be any partitioning of these coefficients here, and they should all be sort of independently determined by their own relationship on y, and not whether or not we include another independent variable. So to demonstrate the effect, we actually get some quite interesting statistical properties. To demonstrate the effect, I'm just going to run some simulations using Python. I'm going to move over to a Jupyter Notebook. So I'm going to import three packages, NumPy just for handling matrices and numbers. We've got a linear regression algorithm from sklearn, and we've got a plotting package, matplotlib. I'm just going to import that. And I'm going to create some data now. So this is all simulated data. And I'm going to create our principal variable that we're interested in, x. And I'm just going to say that's a random, normally distributed variable with a variance of 1 and a mean of 0. And this here describes the array shape. So I'm going to say it's got a sample size of n, and it's an n by 1 vector. So I'm going to also create some other variables, these other control variables. Actually, I'm just going to duplicate them like this. And I'm going to call them a, b, c, and d. These are all independent, so this again corresponds with the graph we just saw. And I'm also going to create the outcome variable y, which I'm going to, in a very simple way, state is just the linear sum of all of these independent variables, plus some of its own random noise that is mean 0 and variance of 1. So again, this simulates a data set. I don't actually generally have access to this true generative structure, but we're defining it for the purposes of simulation. And I'm going to say that my sample size n is 2000. It's quite large. We might want to bump that up. You can play with that. And I'm going to create an object. If you're not into Python, don't worry about that. But I'm basically going to create a linear regression algorithm. And I'm going to fit it to x input the input variables to my linear regression and y. Now we need to define the input variables. And for the first run, even though I know that I've created this variable y as the linear sum of all these variables, I'm just going to run the regression of just x. Oh, I actually missed out x from this. I'm going to create run the regression with just x in the model. And what I want to see really is this linear regression give me an estimation for the coefficient of 1, because the coefficient, I haven't written them in here, they're all equal to 1. You can put 1 times x, 1 times a, 1 times b, 1 times c, and 1 times d. And if I access this coefficient here as follows, I should get it spitting out an estimation of approximately 1. So if I run it, I get 0.998, so very close to 1. And what it might be interesting to look at is how this number varies, and we can get a distribution across these estimations of the coefficient by repeating this, what I've just written. Let's say, well, actually, what I'm going to do is I'll make this 20,000, and then I'll do this 2,000 times. So I'll say for I in range 2,000, then I'm going to run this. So this is a big sample size now, quite a lot larger than most sort of social science studies, for instance. And I'm going to want to store the output of this linear regression coefficient here for each run. So I'm going to create a variable, a list, which is going to be called xcoef no controls, because I'm not including any of the controls data in my model for now. It's an empty list, and for each run, I'm just going to append to that list this coefficient output. And just for ease, I'm going to turn this into an array after it's finished running, and I'll set that running. Right, so whilst that's running, I'm going to write a sort of plot function. So I want a histogram, and I want to look at the values of the estimates for the coefficient on x. I'm going to give it, say, 20 bins. I'm going to make it see-through, and I'm going to set its color to, say, blue for now. And I want to set the range on the x-axis to, say, be between 0.9 and 1.1. We know it should be around 1, but this will just help us sort of narrow in and keep the scale consistent. So when I run this, I see the following. I do get a distribution as I expected, and it does seem to be centered on 1. In fact, if you increase the number of runs, I've kept the number of runs short just to make sure it runs quickly. But if you increase the number of runs, you'll see this center even more strongly on that value 1. So interestingly, if we were to say run exactly the same thing, but remove these variables from the original generation of y and run that, then we get an even more tightly packed distribution of the estimation for the coefficient on x. And you'll see this pop out in a sec. And the reason for this is sort of intuitive. You can see that the variance on this is smaller than the variance here. The reason for this is sort of intuitive. You know, we haven't actually added all these random variables to the generation process here. So now not only does our regression model directly reflect the true data generating process, but we've also removed the noise associated with these additional variables. So that kind of makes sense. So I'm just going to remove that. That sort of gave us something not so surprising. But now what I'm going to do is I'm going to run this at the same time. I'm going to run this and collect data for when I do include the control variables. So I'm going to create an empty list here for now the coefficient on x when we do include the control variables. And for this, I'm going to have to redefine these lines here such that the input to the linear regression is now a concatenation of x with the control variables a, b, c, d as follows. I'm going to concatenate it across the first axis, and that means that I run the linear regression again for every run, and then I'm going to now append the output but to my other list without controls, and then I'm going to do the same here. And I'm going to run that. So whilst that's running, I'll just create the code for plotting it. So now we've got both the distribution across the estimation for the coefficient on x without any control variables included, and then the same for when they are included. I'm going to change the color of this to red. And then we're going to be able to look at how the distributions across these controls varies. So that's finished running. I can plot this. And so something quite interesting emerges. So now our generative model our generative structure, the true generative structure, sorry, is now exactly the same as our linear regression. So the true generative structure is a linear sum of all these control variables, but now we're also including those control variables in our linear regression. And the inclusion of them actually results in a more efficient estimator. So what that means is essentially that we converge and there's less variance to the true value with less variance across each run when we do include the coefficients in the model. So I think this is quite interesting, and it suggests that if you have access to these variables and you have a lot of strong sort of prior knowledge and domain knowledge to suggest that they are indeed completely independent of each other, in reality, obviously, you'll get sort of spurious correlations popping up between these variables, then the inclusion of them in the model can actually yield a lower variance across runs. So what I want to do now is essentially exactly the same thing, but I'm going to reduce the sample size considerably and then compare the results for a much smaller sample size. So we're going to stick with 2,000 runs, but I'm going to reduce the sample size to 200, which is much more typical of, say, a social science study that you might encounter fairly regularly. So now plotting this, the variance is much larger. I need to change my x limits. But the same effect is true. So now, because we've got a much smaller sample size, the estimation on the coefficient of x varies hugely. You know, sometimes it's down here at 0.5, sometimes it's up here at 1.5. Obviously, this distribution is normal for all intents and purposes, and is centered, and theoretically, and is centered on the true value 1. And we still get this dramatic reduction in variance when we include the other coefficients, the other control variables in the model. So the conclusion that I would take away from this is, so long as you have strong domain knowledge and strong prior knowledge that the variables that you have access to, the control variables, are indeed independent of each other, and that there is no other more complicated generative structure, as we might have seen in this other scenario here, then the inclusion in the model can actually help you yield a more efficient estimator. The trouble is often that you don't know the true generative structure, and that when you try and, estimate whether or not these variables are truly independent of each other, as drawn or indicated in this diagram here, you may be subject to sort of the whims of spurious correlations. So judging whether or not they truly are independent becomes very difficult, both statistically and potentially also given your domain knowledge. But if you do know, and if you are confident that they are independent, then the inclusion of those variables in the model does not affect your estimation of the expectation of x, i.e. the average value of the coefficient on x, but it does affect the variance of the estimation of the coefficient of x. And you can see this here. There's a much larger variance in blue here when we don't include the control variables than when we do include the control variables. That all being said, I would strongly suggest against considering controlling for things and take a more nuanced approach via adjustment sets for causal inference. Even if you're not sort of making causal inferences, it does allow you to get more reliable estimates of the things that you're actually interested in, which, if we admit to ourselves, are probably somewhat causally dependent. All right, thank you. I hope that video was useful. Let me know if there are any questions.